In this video, I'm going to talk about the oxoanions of the halogens and use them as a tool to teach you how to assign oxidation states based on Lewis diagrams. So we know that halogens exist in nature in anion form. And in the case of fluorine, that means you're looking at fluoride. Chlorine exists as chloride. Bromine exists as bromide. And iodine exists as iodide, but it also exists in nature in oxoanion form, meaning in the form of an iodine atom surrounded by multiple oxygen atoms with an overall negative charge. Oxoanion is quite literally oxygen-containing anion, and they all have one atom in the middle surrounded by some number of oxygen atoms and a net negative charge. And so one of the most common forms for iodine to exist in nature is actually as an iodate ion, which is different from the iodide ion, the I-. Now, it turns out that iodine is not the only halogen that can form oxoanions. All of the halogens can form oxoanions, and the three larger halogens, chlorine, bromine, and iodine, can form a variety of different oxoanions, whereas, as we'll see shortly, fluorine can only make one. So when you have an oxoanion of a halogen, that tends to put a strong positive oxidation state on the halogen atom. Now, what is an oxidation state? I'm pretty sure that you will have learned about oxidation states in high school, and you will have used them as a tool for measuring electron movement in redox reactions, possibly in the context of talking about electrochemistry. And that's exactly what oxidation states are. They are a tool. They are a counting mechanism. They're not things that really exist. They're just an easy way of comparing the amount of electron density on a reactant versus on the same atom in a product. And so if, for example, I want to look at that iodate ion, that IO3-, if I wanted to draw a Lewis diagram for it, then I'm going to have 7 electrons for my iodine, 3 oxygens at 6 electrons each is 18 electrons, and then I have a -1 charge, so that's 1 more electron, and that's going to give me a total of 26 electrons. You always have the non-oxygen atom in the middle and the oxygens around, so in this case I'm going to put 3 oxygens around my iodine. That uses up 6 of those 26 electrons, and if I fill electrons in around the oxygens on the outside, then that's going to use up almost all of my electrons. I have 2 left, so I put them on the central iodine atom as a lone pair. And this looks fantastic from an octet rule perspective. If I want to keep my Lewis diagram looking like this, I am, however, going to have to add formal charges. And we know that we count formal charge by imagining breaking each of those bonds perfectly evenly down the middle and giving 1 electron to each atom, which would then give each of those oxygen atoms 7 electrons when a neutral oxygen has 6. So it would put a -1 formal charge on each of the 3 oxygen atoms. And then the iodine atom in the middle would get 1, 2, 3 electrons from those 3 bonds, plus the 2 it's not sharing is 5, but a neutral iodine atom has 7 electrons. So this is 2 short of that and gives it a formal charge of +2. And so when counting formal charge, we treat each bond as 100% covalent. So we always give 1 electron to each atom. And we could minimize the formal charge and we would get a Lewis diagram with a couple of double bonds in it and still a -1 formal charge on one of the oxygen atoms. And that would be fine as well. We'd have 3 different resonance structures. They would all look lovely. And we would get exactly the same oxidation state from those Lewis diagrams as we're going to get from this Lewis diagram. So if I want to use my Lewis diagram to calculate oxidation state, I need to start with my Lewis diagram again. And I will start with that version there. Now, when I'm counting oxidation state, instead of breaking each bond as if it was 100% covalent, I'm going to break each bond as though it's 100% ionic. And what that basically means is if there is a more electronegative atom, it's getting both electrons from the bond. So I better take my charges off before I confuse the issue. So what I'm going to do here then is oxygen is more electronegative than iodine. So oxygen gets both electrons from the oxygen-iodine bond. And the same thing happens over here. And the same thing happens down here. And so I can now calculate my oxidation states for the iodate by looking at how many electrons each atom has in this picture compared to how many they would have in a neutral atom. A neutral oxygen atom has 6 valence electrons. We're seeing 8 on each of those. That's 2 electrons too many. So we're seeing oxidation states of -2 on each of our oxygen atoms. And our iodine atom, if it was neutral, would have 7 valence electrons. This one's only got 2. So this iodine atom here has an oxidation state of +5. What does the ion really look like? Somewhere in the middle, but somewhere in the middle is really difficult to calculate precisely. Whereas oxidation state was easy to calculate and formal charge was easy to calculate, and they're both really useful tools in their correct, appropriate context. So formal charge we use to assess whether or not we're happy with our Lewis diagrams. Oxidation state we'll use to measure whether atoms have gained or lost electrons in a reaction. We can determine both by looking at a Lewis diagram and imagining what would happen if we broke the bonds 100% covalently to get formal charge or 100% ionically to get oxidation state. So I mentioned that fluorine can only make one oxoanion, whereas the other halogens can make multiple oxoanions. And if we start trying to draw Lewis diagrams for them, we'll see why. We'll start with the simplest oxoanion, in which you would have one oxygen atom. So we would have a fluorine atom, and we would have one oxygen atom. And we would have complete octet around each. So we've got a net charge of -1. So we've got our fluorine with 7 valence electrons, our oxygen with 6 valence electrons, and that -1 charge gives us 1 extra electron, which gives us 14 electrons. And we can see we've already drawn the correct Lewis diagram there. And if we want to assign formal charge, we have a -1 formal charge on the oxygen. Now for oxoanions, it's always the non-oxygen atom in the middle. So if I wanted to do FO2- instead of just FO-, then I would put my fluorine in the middle. I would attach an oxygen on either side. So now I have 2 oxygens, which means I have 12 electrons, which means I have 20 electrons total for my Lewis diagram. And if I fill them in like so, I have 20 electrons, everything obeys the octet rule. But when I start to apply formal charge, I see that again the oxygen atoms have formal charge of -1. But I have to put a positive formal charge on my fluorine, and I don't like to put a positive formal charge on fluorine. It's the most electronegative element on the periodic table. It is not okay with a positive formal charge. And the only way I could fix that would be to make a double bond. So pick up one of the pairs of electrons on one of my oxygens, push it in toward the fluorine. I have now made the fluorine neutral, which is good, but I have also made the fluorine have more than a complete octet, which is not allowed for an element in the second row of the periodic table. So I can't do that either. So I simply cannot make a decent Lewis diagram for FO2-, and it gets worse as you add more oxygen atoms. Fluorine is not a good enough electron donor to react with enough oxygen atoms to make any oxoanion with more than one oxygen atom. It is not okay with having a positive formal charge, and it is not okay with going over a complete octet. And so we only get one oxoanion for fluorine, whereas all of the other halogens are bigger. And so they are less electronegative, they are more amenable to having the positive formal charge, and or we can pull electron pairs in from the oxygen atom to draw a double bond. Now, if we wanted to assign oxidation states to the atoms in that hypofluorite ion, we would follow the same process as on the previous page, draw out our Lewis diagram, take the bond, break it, give both electrons to the more electronegative atom, which in this case is not oxygen, it is fluorine. Fluorine is the only element on the periodic table that is more electronegative than oxygen. And so as a result, we wind up with an oxidation state of -1 on the fluorine and an oxidation state of 0 on the oxygen atom, which is different from every single other oxoanion of every single other element, because in all the other oxoanions, oxygen has an oxidation state of -2 because oxygen is the more electronegative element. So this is a rather unique oxoanion because the oxygen does not have an oxidation state of -2. Because fluorine is more electronegative than oxygen. And it's the only thing that's more electronegative than oxygen. And the counterpart here would be the fluorine has a negative oxidation state, whereas in all of the other oxoanions, the central atom has a positive oxidation state. So now it's your turn to practice assigning some oxidation states. So I'm going to ask you to draw Lewis diagrams for the 4 oxoanions of bromine. So that means you're looking at BrO-, BrO2-, BrO3-, and BrO4-. May as well get some practice with Vesper, so identify the molecular geometry for each of those ions, and then calculate the oxidation state. So pause the video while you do that, and when you're done, unpause, and I'll work through them. So we start off with the hyperbromite ion, BrO-. It has 2 atoms. So we have a bromine atom with 7 valence electrons, an oxygen atom with 6 valence electrons, a -1 charge adds 1 more electron, and that gives us 14 electrons. And so we used 2 to make the bond. We put the other 12 around the atoms as lone pairs, assign formal charge, and we get a Lewis diagram that looks like that. Not much point in assigning molecular geometry to something that only has 2 atoms. By definition, it's going to be linear because the only way to connect 2 points is with a line. The Lewis diagram for BrO2-, the bromite ion, will have bromine in the middle and then an oxygen on either side. We now have 2 oxygen atoms. So we've got 12 electrons from them, add the 8 from other sources, and we are at 20 electrons. And if we use them to fill in the oxygens and then put 2 lone pairs on the bromine atom, everything obeys the octet rule. If we leave our diagram like this, we need to put a -1 formal charge on each of the 2 oxygen atoms and a +1 formal charge on the bromine. Or if you prefer, you could reduce the formal charge, minimize the formal charge, and bring a lone pair from one of the 2 oxygen atoms in to make a double bond to the bromine, recognizing, of course, if you do this, there are 2 resonance structures, because it really doesn't matter which of the two oxygen atoms you pulled that electron in from. And whether you left your Lewis diagram obeying the octet rule with the higher formal charge, or whether you minimized formal charge to get one of these two diagrams, you will still obtain the same geometry. It's the tetrahedral electron group geometry, and specifically, we are looking at a molecule that is bent. 2 lone pairs, 2 bonds is bent. Same process for bromate. We have a bromine atom with 3 oxygen atoms around it. That means we're going to have 18 electrons coming from those oxygen atoms. Add the 8 electrons from other sources, and we have 26 electrons, which we can use to fill in all of our atoms and get them obeying the octet rule. And if we want to have everything obey the octet rule, then we're going to wind up with a +2 formal charge on the central bromine atom, and that's fine. If you prefer to minimize formal charge, then you would bring in a lone pair from 2 of the oxygen atoms, doesn't matter which 2, and you will therefore wind up with 2 double bonds and a single bond, and the single bonded oxygen atom will show a -1 formal charge. Again, there will be resonance structures. In this case, there will be 3 resonance structures, and I don't have space to show all 3 of them, but recognize that the true picture would be an average of those. And if we look at this molecule, we can see that it has a trigonal pyramidal geometry. It is also tetrahedral electron group geometry, but 1 lone pair means trigonal pyramidal molecular geometry. And then finally, the perbromate ion has 4 oxygens around the bromine. So 4 oxygen atoms at 6 electrons each is 24. Add the 8 from elsewhere, gets us 32 electrons. And if we fill in lone pairs around all of the oxygen atoms, that uses our 32 electrons. In that case, we would have -1 formal charges on each of the 4 oxygens, and we would therefore have a +3 formal charge on the bromine. That's your obeys the octet rule Lewis diagram. If you want to minimize your formal charge, you will then pull in lone pairs from 3 of the 4 oxygen atoms. It does not matter which 3, but if you're going to start minimizing formal charge, minimize it all the way. Don't go halfway. Don't pull in 1 or 2 lone pairs. If you're minimizing formal charge, minimize it. Get to this. And we can see that we have 4 electron groups around our bromine atom. And so whether or not you minimized your formal charge, you get the same molecular geometry either way. And regardless of whether you chose to minimize your formal charge or leave your Lewis diagrams obeying the octet rule, you will also get the same oxidation state. So to determine the oxidation state in bromine, we look at each of the Lewis diagrams and we imagine breaking all of those bromine-oxygen bonds so that all the electrons go to oxygen, because oxygen is more electronegative than bromine. And so if I wanted to calculate the oxidation state for bromine in the hypobromite ion, then I break that bond, give the electrons to the oxygen. I still have the 3 lone pairs on bromine, so that's 6 electrons left. And therefore, it has an oxidation state of +1. If I do the same thing for the bromite, the BrO2-, give all of the bonding electrons to the oxygens because oxygen is more electronegative, I'm left with 4 non-bonding electrons, the 2 lone pairs on the bromine. Neutral bromine has 7 valence electrons. This is 4. That's 3 less than that. And so the oxidation state of my bromine in BrO2- will be +3. Do the same thing for bromate. And now my bromine only has 2 electrons left, which is 5 less than the 7 that a neutral bromine atom would have. And so that's an oxidation state of +5. And do the same thing for the perbromate ion. Nothing left on the bromine. That's 7 valence electrons less than a neutral bromine atom would have. And that is an oxidation state of +7. And I will remind you that oxidation states don't actually exist, but we can see that if we did a reaction in which we started with hypobromite, BrO-, and ended up with perbromate, BrO4-, we could reasonably comfortably say that the bromine atom had become more positive throughout that reaction. And that's what we use the oxidation states to show. A increase in the amount of electron density or a decrease in the amount of electron density. Did the atom become more positive? Did the atom become more negative? And since the halogens are relatively electronegative elements, they tend to be very reactive when they have large positive oxidation states. They tend to prefer to undergo reactions that will make them have less large positive oxidation states. And so therefore, looking at these 4 ions, the perbromate, the BrO4-, is going to be the most reactive. It is going to be the species that is the best at gaining electrons so that other things can lose them, so that other things can be oxidized, making it the best oxidizing agent of this set of species. It's the one that wants to gain electrons the most. It is therefore the best oxidizing agent and the most reactive of these 4 ions. The next most reactive, maybe no surprise, the bromate, BrO3-, and then bromite, BrO2-, and then the hypobromite, BrO-. As the bromine atom becomes less positive, it becomes less reactive. So I've been using the names of various oxoanions throughout this video, and this table shows you the names for which you're responsible, the naming system you need to understand. Now, I don't personally think it's all that helpful to flat memorize this table. What you do need to memorize is you do need to memorize what I will call the 8s. And so that would be the chlorate ion, the nitrate ion, the carbonate ion, the sulfate ion, and the phosphate ion. And you need to know the number of oxygen atoms, and you also need to know the charge. And if you fully protonate any of those, you will get the corresponding ic acid. So sulfate, SO4 2-, if you add 2 protons, you get to sulfuric acid, H2SO4. And you should know that sulfuric acid is H2SO4 already. Now, as long as you know the 8s cold, you can do everything else by relation to them. You will notice, for example, on this table, that sulfite has 1 less oxygen atom but the same charge as sulfate, and phosphite has 1 less oxygen atom but the same charge as phosphate. Nitrite, 1 less oxygen atom than nitrate, same charge. Chlorite, 1 less oxygen atom than chlorate, same charge. So you remember the 5 8s, and you remember that if it's ite, there's 1 oxygen less. Hypochlorite has 1 oxygen even less than that, because hypo means not enough. Hypoglycemics have low blood sugar. Perchlorate, on the other hand, has 1 more oxygen atom than chlorate. And per is short for hyper, but that hype is not actually part of the name. And we know that if somebody is hyperactive, that they are highly active or more active. And so hyper refers to more, and perchlorate has more oxygens in it. And then the last point to remember is that if you partially protonate your ions, so if you add a single proton to something with a -2 charge or to something with a -3 charge, then you reflect the addition of that proton by adding the word hydrogen in front. So, for example, if we were to have a proton and add it to CO3 2-, we would get HCO3-, and so The CO3 2- is carbonate, the H+ is hydrogen, and the H